Let's try a thought experiment. You ask an AI model to research the best marketing strategy for a new product launch. It gives you a solid answer based on its training data. Done. Now here's a different version. You tell an AI the same goal, research the best marketing strategy for a product launch. But this time, it has access to a search tool. So, it runs a search. It reads the results. It decides it needs more context, so it runs another search, narrowing the query based on what it learned. It finds a relevant competitor case study. It runs a third search to verify a statistic it suspects might be outdated. Then it synthesizes everything it found and drafts a recommendation. And then it reviews its own draft and decides one section needs more supporting evidence before it can be confident in the claim. So, it searches again. What's the difference between those two scenarios? The first one is a language model doing what language models do, generating a response from what it knows. The second one is an agent. It's not just generating a response, it's taking a goal, planning how to achieve it, using tools to interact with the world, observing the results, updating its plan based on what it finds, and looping through this cycle until it decides it's reached a satisfactory outcome. This is a fundamentally different kind of system, and understanding what makes it different and what actually makes it work is essential for anyone building serious AI applications. Let's start with the foundational question. What are the actual components that transform a language model into an agent? Think about what makes a human being capable of completing a complex task over time. They have access to tools, a phone, a computer, a library. They have memory. They remember what they've done and what they've learned. They can plan, break a large goal into smaller steps and sequence them. And they can iterate, act, observe what happened, update their approach, and try again. An AI agent is defined by the same four properties. Take any one of them away and you no longer have an agent. You have something simpler. The first property is tools. An agent can interact with the world beyond the content of its training data. It can run web searches, execute code, read and write files, call APIs, query databases. Each tool extends the agent's reach into live, external information and systems. Without tools, the model is sealed in a room, very intelligent, but only able to reason about what it already knows. The second property is memory. An agent maintains state. It remembers what it has done and what it has encountered across the course of a task, not just within a single exchange, but potentially across multiple sessions. Memory is what allows an agent to build on its own prior actions rather than starting from scratch at every step. The third property is planning. An agent can decompose a high-level goal into a sequence of subtasks and reason about the best order to execute them. It can look at the objective, ask, "What would I need to know or do to achieve this?" construct a plan, and adapt that plan when new information changes the picture. Planning is what separates an agent from a reactive system. A reactive system responds to inputs. A planning system pursues goals. The fourth property is the task loop, sometimes called the reason, act, observe cycle. The agent reasons about what to do next. It takes an action. It observes the outcome. It updates its understanding based on what it observed. Then it reasons about what to do next again. This loop continues until the agent reaches a stopping condition. Each iteration of the loop is one step forward toward the goal. Complex goals may require dozens of iterations. The loop is the engine.
So an agent has four defining properties: tools, memory, planning, and task loops. But of those four, memory is often the least well understood and the most important to get right. Let's go deeper into the different types of memory an agent can use and why each one matters. Think about your own memory system for a moment. You have immediate working memory, what you're actively thinking about right now in this moment. You have long-term memory, knowledge you've accumulated over years, stored somewhere in your brain and retrievable when you need it. And you have episodic memory, specific experiences you've had, what occurred during them, and what you learned as a result. An AI agent has equivalent memory systems, and they serve different functions at different timescales. The first type is in-context memory. This is the most metal big memory and task loops, and then more frequently wants comfort. The first type is in-context memory. It's the content actively present in the model's current context window, the instructions you gave it, the tools it has available, the results of actions it has already taken in this session, the reasoning it has written out. In-context memory is fast, immediately accessible, and highly detailed. The model can reference anything in its context window with full precision, but it has a critical limitation. It's temporary. When the session ends, in-context memory is gone, and it's bounded by the context window limit. Once you exceed it, earlier information starts falling out of scope. This is why agents often think out loud in their responses, writing out reasoning steps, intermediate conclusions, and observations. They're not being verbose for its own sake. They're writing to their own memory so that their earlier reasoning remains visible and usable in later steps. The second type is external memory. This is long-term storage that lives outside the model, in a database, a file system, a vector store. When an agent needs to recall something from a previous session or needs to access knowledge that exceeds its context window, it queries external memory. In practice, external memory for AI agents is often implemented using what are called vector databases, stores that hold text as mathematical representations, vectors, and can retrieve semantically relevant content based on a query. An agent can search its external memory the same way you'd search Google, not by looking for exact keywords, but by querying for conceptual relevance. External memory is what gives an agent persistence across sessions. Without it, every new conversation is a blank slate. With it, an agent can remember your preferences, the projects you're working on, the decisions you made last week, and the context you've shared over time. The third type is episodic memory. This is a record of the agent's past task experiences, not just knowledge, but the history of what the agent did, what happened as a result, and what it could infer from the outcome. Episodic memory allows an agent to learn from experience. If a particular strategy failed 3 times and succeeded on the 4th attempt, episodic memory holds that history. The agent can reference it. Last time I approached this kind of task with strategy A, it failed. Let me try strategy B instead. This transforms the agent from a system that runs tasks to a system that improves through iteration.
Understanding what an agent is and how it remembers things is foundational. But there's a practical question that every agent has to answer at every step of its task loop. And getting the answer wrong is one of the most common failure modes in agentic systems. When should the agent keep going, and when should it stop? Imagine you hired a contractor to renovate your kitchen. You gave them a clear brief and a budget. You came back 3 weeks later and found the kitchen beautifully renovated. But the contractor had also, without asking, redesigned your living room, repainted the hallway, and replaced the front door, because they thought it would improve the overall aesthetics of the house. Same quality work, but a complete overstep on scope. You asked for a kitchen, you got a full house renovation, plus an unexpected invoice. This is exactly what happens when an AI agent lacks clear stopping conditions. It pursues the underlying goal beyond the boundaries of the task you defined. It keeps acting and optimizing and taking steps because nothing explicitly tells it to stop. Stopping decisions in an AI agent are governed by 2 kinds of conditions: completion conditions and uncertainty thresholds. Completion conditions are explicit criteria that define when the task is done. A well-designed agent prompt specifies, clearly, what constitutes task completion. Not vaguely, when you've done enough research, but precisely. Stop when you have found at least 5 peer-reviewed sources addressing the topic, or when you have executed 10 research actions, whichever comes first. The number of actions limit isn't arbitrary. It's a safety guardrail. Without it, an agent with a search tool can theoretically run thousands of search queries in pursuit of the perfect answer. API costs accumulate. Time accumulates. The agent may eventually time out, produce nothing, or produce output so over-researched it's no longer useful. Hard limits prevent runaway loops. Uncertainty thresholds address a different scenario. Not, is the task complete, but should the agent continue autonomously or ask for human input? A well-designed agent distinguishes between situations where it has sufficient confidence to act alone and situations where critical information is missing or the stakes are high enough to warrant human review before proceeding. This is called a human-in-the-loop condition, and building these into agent designs is one of the most important safety practices in agentic AI. A practical example: an agent managing a marketing campaign might be authorized to make autonomous decisions about ad copy adjustments and targeting changes up to a certain spend level. But if a recommended change would exceed that budget, the agent should pause and surface the recommendation for human approval before executing. The threshold isn't, can the agent do this? It's, should the agent do this without a human checking first? There are 4 standard patterns for how agents handle these moments. First, continue autonomously. The agent has sufficient confidence, the action is within scope, and the stakes are low. Second, request clarification. The agent explicitly asks the user for more information before proceeding. Third, escalate. The agent flags the situation for human review and waits. Fourth, abort and report. The agent determines it cannot safely complete the task with the available information and ceases, explaining what it encountered and what would be needed to proceed. Designing these patterns explicitly into your agent prompts before the agent encounters an ambiguous situation is the difference between an agent that handles uncertainty gracefully and one that either stops without explanation or barrels forward into a mistake.
We've covered what makes an agent: tools, memory, planning, task loops. We've covered how agents remember across different timescales. We've covered how they decide when to stop. Now let's address the question that often creates the most confusion for people first learning this territory. On the surface, chains and agents can look similar. Both involve multiple AI steps. Both can use tools. Both can produce complex outputs. So what's actually different between them? The distinction is this: a chain follows a fixed structure. An agent follows a goal. Let me unpack that. In a prompt chain, the workflow is predetermined. You've decided in advance. Stage 1 does X, Stage 2 does Y, Stage 3 does Z. The structure of the pipeline is fixed at design time. When you run the chain, it executes exactly those stages in exactly that order. The model generates content at each stage, but it doesn't decide the structure. You decided it. In an agent, the structure is dynamic. The agent receives a goal and then decides, at runtime based on what it discovers, what actions to take and in what order. It might take 3 steps. It might take 15. It might change direction midway when it encounters information that changes the picture. The specific path through the task is not predetermined. It emerges from the agent's own reasoning process. This is the conceptual leap. A chain is a defined process that executes. An agent is a reasoning system that plans its own process. Imagine the difference like this. In a chain, you give a person a recipe and they follow it. In an agent setup, you tell a chef, "Make me a delicious dinner," and they decide what to make based on what's available, what you told them about your preferences, and what their experience suggests will work. They might go to the store mid-preparation if they're missing an ingredient. They might change the entire menu plan when they discover the main ingredient isn't fresh. They're navigating toward a goal, not executing a script. So when should you use a chain versus an agent? Use a chain when the task has a well-understood fixed structure. You know exactly what stages are needed, in what order, every time. The input domain is predictable. The output format is specified. You value reliability and controllability over flexibility. A well-designed pipeline will outperform an agent for structured, repeatable tasks. It's faster, cheaper, and more debuggable. Use an agent when the task requires dynamic decision-making.
The scope of the work isn't fully known in advance. The path to completion depends on what the agent discovers along the way. The task involves navigating the real world via search, code execution, or API calls, rather than processing a predetermined input. You need the system to adapt. Here's an important practical insight. Most production AI systems are neither pure chains nor pure agents. They're hybrid architectures. An orchestrating agent receives a high-level goal, breaks it into structured subtasks, and hands those subtasks to pipelines that execute them reliably. The agent provides adaptability at the top level. The pipelines provide reliability at the execution level. This combination, adaptive reasoning at the orchestration layer, reliable execution at the task layer, is the architecture behind many of the most capable AI systems being deployed today. Let's consolidate everything from this lesson. An AI agent is defined by 4 properties: tools that let it interact with the world, memory that lets it maintain state across steps, planning that lets it decompose goals into actions, and task loops that let it reason, act, observe, and iterate toward completion. Memory operates at 3 levels: in-context memory for immediate working awareness, external memory for persistent knowledge across sessions, and episodic memory for learning from past task experiences. Agents decide when to stop based on completion conditions and uncertainty thresholds. And well-designed agent prompts include explicit human-in-the-loop triggers for situations where autonomous action carries significant risk. And the defining difference between a chain and an agent is structure versus goal direction. Chains execute a fixed process. Agents navigate dynamically toward an objective. You now have a clear conceptual map of what an AI agent actually is. In the next lesson, we move from concept